Revolutionizing ultrafast lasers, a breakthrough technique for power and precision. Imagine a world where lasers can cut through materials with unparalleled precision or illuminate microscopic details with stunning clarity. That's the promise of ultrafast lasers, and we're about to take you on a journey to explore a groundbreaking technique that could transform the landscape of laser technology. But here's where it gets controversial. This innovation hinges on mastering the dance of light within multimode fibers. In the quest for higher power lasers, scientists have traditionally relied on single-mode fibers. However, these fibers hit a ceiling when it comes to energy output due to fundamental physical limitations. Enter multimode fibers, which can carry multiple light modes simultaneously, offering a tantalizing solution. This technique, known as spatiotemporal mode locking, STML, holds the key to unlocking higher power levels. And this is the part most people miss. Our team has taken a significant step forward in overcoming the challenges of STML by developing a novel approach to precisely control each light mode independently. This breakthrough not only boosts laser power, but also enhances its versatility, setting the stage for a new era of ultrafast lasers. The crux of the matter lies in intermodal dispersion, a phenomenon where different light modes within a multimode fiber travel at varying speeds. This speed difference causes laser pulses to spread out, thwarting the creation of stable, high-power pulses. Previous attempts to address this issue often involved spatial filtering, which unfortunately restricts the number of modes that can be synchronized, limiting power gains. To tackle this conundrum, we've introduced a transverse modes division control technique. It's a simple yet ingenious method that involves using a mode multiplexer demultiplexer, DEMUX, to segregate the mixed beam into individual channels, each dedicated to a specific mode. Once isolated, we can adjust the dispersion for each mode separately by introducing precise lengths of compensatory fiber to each channel. This allows us to optimize every mode before recombining them into a single, powerful, and coherent beam. Theoretically, this method enables us to synchronize an unlimited number of modes, maximizing the fiber's energy potential. We put our technique to the test in a Figure 8 YB-doped all-fiber, spatiotemporal, mode-locked laser setup. The results were nothing short of remarkable. By synchronizing 4 transverse modes simultaneously, we achieved dissipative soliton pulses with 15 nanojoules of energy at a repetition rate of 14.49 MHz. The output power scaled directly with the number of participating modes, demonstrating a slope efficiency of 7.9% when 4 modes were locked, significantly surpassing the 3.79% efficiency of single-mode operation. Moreover, our technique opens up new possibilities for beam shaping. By dynamically selecting the combination of modes involved in the mode locking process, we managed to generate a quasi-flat top beam with a uniform intensity profile. This specialized beam boasted an average output power of 150 milliwatts and a single pulse energy of 10.4 nanojoules at a pump power of 3 watts. Our laser also showcased exceptional long-term stability, with minimal frequency drift even after 12 hours of continuous operation. In summary, we've developed and experimentally verified a revolutionary control technique that addresses the core challenge of power scalability in STML fiber lasers. By independently controlling the dispersion of each transverse mode, our method paves the way for synchronizing any number of modes and maximizing energy extraction. This universal framework for multi-mode spatiotemporal dynamics control promises to usher in the next generation of ultra-fast light sources with far-reaching implications for precision fabrication, nonlinear microscopy, and attosecond science. So, what do you think? Could this breakthrough in laser technology change the game for industries ranging from manufacturing to medical imaging? Share your thoughts in the comments below.